Hello, everyone. I'm Yuanda Wang. I'm a PhD student from Michigan State University, and I'm glad to share our work, VSMask, defending against voice synthesis attack via real-time predictive perturbation. This work is done with my landmates, Hanqing, Guangjing, Bocheng, and my advisor, Dr. Qiben Yan. Let's get started. So voice synthesis technology has rapidly advanced in recent years, allowing the creation of synthetic voices that sound incredibly realistic. For example, we can speak some words and make it sound like Obama. So this voice synthesis can be applied in multiple applications. Like Amazon is developing a product to read stories with real human voice, or you can let your favorite movie star lead you in the navigation applications. And there are two types of voice synthesis methods. The first one is voice conversion. We have a speech sample from ambient speaker to provide the speech content, and another speech sample from the target speaker, as shown in the blue waveform. And then the content is encoded by the content encoder EC, and the target speaker's voice pattern is encoded by the speaker encoder ES. So finally, the decoder will combine the content and voice and output a synthetic speech with the content in speech sample P, but sounds like the voice in sample X. And the other one is text to speech. The only difference between these two is that text to speech does not provide content from a speech, but it can directly extract the content from an input text T. However, even voice synthesis technology can be utilized in many benign cases. Recently, there are lots of security threats caused by voice synthesis. The cloned voice is used in scam phone calls to craft human ears. For example, a little girl's voice is cloned by the attackers and launch a fake kidnapping. And we can easily find many similar cases in recent news, which raises security concerns about such deepfake voice. Here, we conclude the threat model of voice synthesis attacks. For the adversaries, it is necessary to have speech samples from the victim speaker. Unfortunately, in real-world scenarios, our voice is exposed everywhere. First, in the real-time communication applications like Zoom or WhatsApp, our speech might be hacked by the attackers. And second, if we upload our videos to social media apps like TikTok or YouTube, your voice is leaked as well. Third, if the attacker can stealthily record your real-time conversation, they can also generate your fake voice. Meanwhile, synthetic speech has caused significant harm in real life. For example, fake voice can control your voice assistant and launch malicious voice commands, or it can be used to bypass speaker verification process. The most threatening case is that it can also be used to spoof human ears and cause financial losses. Now, I would like to introduce the defense measures against voice synthesis attacks. As we introduced in previous slides, both voice conversion and text-to-speech methods, they have a speaker encoder, which is the key component for identity transformation. In this way, if we can fool the speaker encoder, the synthetic speech cannot well mimic the target speaker's voice, and it will fail to compromise speaker verification or human ears. For example, here is a speaker encoder, and if the input speech from the victim speaker is clear, then the voice synthesis will finally generate a synthetic voice sounds like the victim speaker X. As the speaker encoder is a neural network model, it is vulnerable to adversarial speech samples. In this way, if we input an adversarial speech example with perturbation delta, the speaker encoder will be fooled. Here is the optimization process of this perturbation delta. The first part is to make the output close to another voice Y, and the second part is to push the output far from the real voice X. Finally, the output will sound like another speaker Y, but not the real speaker X. However, this defense method still has some weaknesses. First, the existing defense cannot provide real-time protection. But in real-time applications like Zoom, we must immediately send over speech. And second, gradient descent method requires thousands of iterations to optimize the perturbation, which is really time-consuming to generate the protected speech. Third, the perturbation in the protected speech is perceptible, which will degrade the audio quality. To protect our voice in real time, we list some potential solutions. First, random noise can provide protection, but it works only if the noise is very strong. And second, real-time gradient descent is not practical, as the time is very short. It does not allow sufficient iterations. Third, universal perturbation works for some short samples, but it fails to protect long speech. Here comes the question: how to protect our voice in real time without compromising the audio quality? The most challenging part for real-time protection is how to predict the future speech. It is not feasible to predict the speech itself because of the language diversity. But we can use a neural network to predict the most effective perturbation for upcoming speech according to the previous speech. Based on this idea, we propose VSMask. And here is the workflow of VSMask predictive model. We use past speech as the input and convert the time domain signal to a 2D MELF spectrogram. And the predictive model is composed of multiple downsampling rates and upsampling rates. Finally, it will output a spectrogram with the same dimension as the input spectrogram, but much shorter. And next, the MELF spectrogram will be converted back to time domain signal, which works as the perturbation for upcoming speech signal. VSMask can protect real-time speech without time latency. For example, someone is talking, and when VSMask detects the speech starts, it will capture the human speech with length t. And after a short time delay delta t, it will inject the perturbation into future speech. To protect following speech, we only need to slide the input window forward, and the predictive model can iteratively output the real-time perturbation. And this is the predictive model optimization process. Compared with gradient descent method, we only need to optimize the parameters in the predictive model zeta instead of the perturbation delta itself. In this way, we can easily get the best protection performance in real time. However, only the predictive model itself cannot provide sufficient protection. For example, this is a speech sample. Please protect my voice from voice synthesis attack. The later speech can be well protected, but the beginning of the speech is still exposed. To give a complete protection, we add a universal perturbation to indiscriminately protect the beginning of each speech. And here is the optimization process of the universal perturbation header. And we build a training set D and train one universal perturbation delta H on all of the training samples. And finally, we can successfully protect the entire speech by combining the universal perturbation header and predictive model. Next, we would like to mitigate the perceptibility of our protected speech. According to the eco-loudness contour, human ears show different sensitivities for different frequencies. Our ears are more sensitive to frequencies between 1.6 kHz and 4 kHz. In this way, we can add a weighted constraint to the perturbation. So it can help us to reduce the perceptibility in most sensitive frequency bands. In this case, we can see that the constraint epsilon2 is the smallest and epsilon1 is the largest to effectively reduce the perceptibility of our perturbation. VSMask can be deployed in many scenarios. First, in online applications like real-time apps and social media, VSMask can protect your speech data before you upload them. And second, in real-world scenario, you can install VSMask on your mobile device, and when you are talking, VSMask can inject a real-time perturbation signal. Compared with the existing methods, VSMask can achieve real-time perturbation with zero latency and low perceptibility. Next, I will introduce our evaluation setup. We have three different target voice synthesis models. The first one and second one are voice conversion models. The last one is text-to-speech model. And we test VSMask on two datasets for voice conversion and text-to-speech respectively. Also, we compared VSMask performance with some baseline methods like random noise, periodical perturbation, online PGD, and offline PGD. And hyperparameter setup is also listed on the slide. For a male speaker, VSMask can make the synthetic voice sound like a female and vice versa. We use SpeechBrain, an open source tool, as the speaker verification model. And our target model in this experiment is ADA-INVC. And first, we compare the audio quality of the raw speech and protected speech. The STOI is higher than 0.8, which means that the protected speech is still clear enough for human recognition. And next, we compared VSMask with other baseline methods. The results show that VSMask outperforms all other real-time defenses and achieves similar performance as offline PGD method. And next, we evaluate VSMask on all three different voice synthesis models. The left figure shows the similarity score before and after protection. We can notice that VSMask can significantly reduce the similarity between the synthetic speech and the victim speaker. After VSMask protection, none of the synthetic speech can bypass the speaker verification system anymore. And then we evaluate VSMask performance on human ears. We recruit 25 volunteers for human study. And first, we ask them to evaluate the perturbation perceptibility in the protected audio. From the result, we can find that for both voice conversion models, almost 90% of answers consider the perturbation generated by VSMask is negligible or acceptable. And second, we ask the volunteers to identify if the raw speech and the synthetic speech have the same voice. Without perturbation, 80% of answers believe that the synthetic voice is same as the victim speaker. In comparison, when we use VSMask to protect our speech, nobody will be fooled by the synthetic voice, as the voice sounds like a totally different person. Next, we test VSMask performance on cross-model setup. In this experiment, we optimize the perturbation on one source model and evaluate its performance on another target model. The results show that VSMask can still protect most speech samples, but it cannot achieve 100% success rate due to differences between different voice synthesis models. And we also consider some adaptive attackers use different signal processing methods to remove the perturbation. However, as VSMask perturbation is generated in Mel spectrogram but not time domain waveform, it is robust to normal signal processing methods. And finally, we test VSMask performance in real-time scenario, in real-world scenario. We use an iPhone as the eavesdropper and we deploy VSMask on a laptop. While the speaker is talking, VSMask can send the perturbation audio to protect his voice. And we can find that VSMask can provide stronger protection than simple random noise. In this way, we demonstrate VSMask can protect our voice in real physical world as well. We also have some discussions about VSMask. First, we measure the real-time feasibility of VSMask and the time consumption of one computation, including the signal processing and prediction, is less than 200 milliseconds. With a 0.4 seconds time delay, VSMask can achieve real-time protection. And second, we acknowledge that adversarial training is a potential approach to overcome our defense, but it requires several days for training a robust model. Moreover, our defense has some limitations. First, we did not consider more powerful attackers. Like some attackers, they can remove perturbation by diffusion model, or VSMask assumes that we have full knowledge about target voice synthesis model. But in black box scenarios, the performance is degraded. Third, in different environments, the physical world protection performance might be different. Here is the conclusion. We propose VSMask, a real-time defense mechanism against voice synthesis attack based on predictive model. And we optimize a universal perturbation header to indiscriminately protect speech with different lengths and sizes. And finally, we evaluate our defense on 3 different voice synthesis models. The experimental results show that VSMask can provide real-time defense on both digital and physical spaces. Thanks for listening, and I'm ready to answer your questions.
Questions for our speaker? Looks like there's no questions. So in the interest of time, thank you, Yuanda, for that great talk.